ladies and gentlemen, welcome back for another round of chemistry. This is Mr. Doolin. I thank you for tuning in. Today we're going to take a look at ionic formula writing, and specifically what we're going to be looking at in here is our main group metals and our hydrates. I hope you understand by me saying it's ionic that we are going to have metals bonding with nonmetals, right, as a general rule of thumb. Rule of thumb. There you go. And so what we want to do first is we want to define what an ionic formula actually is. So ionic formulas represent the simplest ratio of cations and anions to balance out ionic charges. And so again, it's the simplest ratio of cations and anions to balance out ionic charges, which means we need equal numbers of total positive and total negative. So an example I'll do with you here, or let you look at, is aluminum oxide. It's aluminum bonded with oxygen. And so you'll notice the way that I write my formula, I've got my element abbreviation, right, for both elements, and then the number that I want to definitely make sure that you understand is this bottom number. It's known as a subscript, and what a subscript tells me is actually how many elements are present. And so notice that the subscript to the right, to the bottom right of an element, applies to any given element. So in this particular formula, we would have 2 aluminums and we would have 3 oxygens. Now, for balancing out charges, I want to be very, very, very clear here. Aluminum, based on where it's at in the periodic table, I know has a +3 charge, and then oxygen has a -2 charge as an ion. And so what I'm doing here is I'm looking for a least common multiple, and so if I take this and multiply that times 2, that gives me a total of +6. Multiply this times 3, it gives me a total of -6, and all of a sudden now I have the same number of positive as negative. And notice all I did there was I found the least common multiple between the charges. All right, and if we look, this is actually the simplest ratio, simplest combining ratio when aluminum and oxygen will react, and we are going to refer to it as the ionic formula. Okay, and so I took a break and I actually drew in a periodic table. Hopefully what I want you to do now is pause the video and go ahead and get this sketched into your notes, but we're going to go ahead and start talking about it here. I wanted to specify which group metals that, or which metals are considered to be part of the main group family. And if you've been in my class, you know that we're looking at the 2 major groups here, A group versus B group. And my A groups are everything that appears up above, right? So this is group 1A, group 2A, group 3A, so on and so forth. Transition metals are part of my B group, right? So these are my B group, known as transition metals. And so today when we're looking at writing our formulas, we're going to specifically be looking at using metals from our main group, our A group. And so we want to be referring to main group elements today when we're doing this. All right, just so you understand. And the reason we're going to do that is because main group elements have predictable charges. And so if you remember back from earlier units, we know everything in group 1 is +1, everything in group 2 is +2, everything in group 3 is +3, and then we go plus or -4, that's our seesaw, and then we start hitting -3, -2, -1, and then we say the noble gases don't carry ionic charges. And so understanding where these charges lie, and that we can look at a group that an element falls in and predict an ionic charge for them is very, very important for what we're about to get into, ladies and gentlemen. There are a couple of exceptions to this. There's a couple of elements over here. They are zinc and cadmium, and then also silver is over here, and those actually have very predictable charges even though they are in the B group, right? Everything else, a transition metal, I'm going to have to actually do some work to figure out what the ionic charge is, and we'll get into that later, all right? But zinc and cadmium, they always have a +2 charge. Silver always has a +1 charge. And this will become really important later on as we start tying together all the different types of ionic compounds that we've got. And then there are 2 other groups or 2 other elements that I'm going to look at today, and SN and PB. So that's tin and lead. And tin and lead actually will form either +2 or +4 ions. So something to be completely aware of when we're doing our naming. And will you have to memorize those exceptions? You betcha. All right, and so again, I've erased the page and drawn something here, so take a second, get it written down. But what we're going to do is I want to point out the 3 different types of ionic compounds that we're actually going to learn to name in this particular class. The first one is what we're going to do today, and these are our main group metals and a nonmetal. And we'll learn how to write the formulas based on ionic charges and balancing out those charges. The second type of compound for ionic that we'll look at is when we have transition metals and bonded to a nonmetal, and we have to do a little bit of work with those because the transition metals do have variable charges. We have to look at what they're bonded to a lot of the times to be able to predict what ion they actually formed in that compound. And then the third kind is a metal, and I'm being very, very vague there because that particular metal in the third compound can be either main group or it can be transition metal. But the third type is when we get a metal bonded with a polyatomic ion. And again, polyatomic ions are something that we've introduced before, and hopefully you remember what they are, but we'll definitely look at them and get more in depth with what they are and how to name them and write formulas with them in this particular unit as well. All right? Now, there is a kind of a fourth one that I'm just going to sneak in there, and I'm going to say any of these can form hydrates. I'll say can be a hydrate, right? And what a hydrate is it's when I have an ionic compound that is actually, I want to say bonded, but I don't know if it's actually can be described as bonding, but water has hydrated, it has attached itself around the ionic crystal as a solid, and what we say is that we've got X number of waters attached to the ionic compound, and so this is what a hydrate actually looks like. I've just got an ionic compound with a certain number of waters, and these are actually pretty easy to name and write formulas for, and we'll see an example of that today as well. All right, but understand the definition of a hydrate is when I've got an ionic compound that actually is hydrated with waters. It's got water molecules surrounding in a specific ratio in the compound. Okay, and so what I'm going to do now is I'm just going to walk you through a couple of examples here for how we're going to write these formulas. The first example I'll look at is what if I have a combination of sodium and oxygen? What ionic formula would they form? And again, it's based on charges, so I'm going to find sodium in the periodic table. I know it's in group 1, so it's a +1. Oxygen, I know, has an ionic charge of -2 based on where it's at. And so if I'm going to balance out these charges, I'm looking for a least common multiple here. I know it's 2, and so that means I'm going to have to multiply this guy by 2. And so I'd end up with Na2O. And again, I'm just trying to balance out charges. If I have a total of 2 negatives, I need a total of 2 positives, and so I need more sodiums in that particular case. Now, another way that you may actually be presented this information is I may give you a name, and this is probably going to be the more predominant way you'll see this information, is I'll give you the name sodium oxide, and you need to understand that that's a sodium bonded with an oxygen in an ionic bond because it's metal and non-metal. And again, I just go through the same steps, and I end up in the same place. All right? Okay, so the next example that I'll do is I'll look at aluminum sulfide. Right? And so again, I'm looking at the name. I see metal, non-metal. I know it's an ionic compound. My abbreviation for aluminum is Al. Sulfide is actually referring to sulfur. So notice on the endings of these names, I'm always seeing, or most of the time I'm seeing an IDE ending. I'm just looking for the name that associates with that. All right? So aluminum will form a +3 ion. Sulfur is a -2. So what's the least common multiple between 2 and 3? Well, it's 6. So I'm going to multiply the aluminum times 2, the sulfur times 3, and what that gives me is an ionic formula of Al2S3. Right? And so hopefully you kind of see a pattern here where my charges actually just drop diagonally, or they crisscross, if you will. All right? All right, the next example I'll do with you is calcium phosphide. Okay, and again, an IDE ending tells me it's a singular element. I'm going to look on the periodic table. I know that this is going to be phosphorus, and this one is going to be calcium. Based on where they're at in the periodic table, I've got a +2 and a 3 charge. So again, I've got a 2 and a 3 ratio here. My least common multiple is 6. So I know I'm going to have to multiply my calcium times 3, multiply my phosphorus times 2, and what that ends up giving me as my formula is 3 calciums and 2 phosphorus. So calcium phosphide would be this. Now, I am going to go ahead and just blatantly tell you here, you can actually just cross these. And what that's known as is it's known as the crisscross shortcut. But if you're going to use the crisscross shortcut, I need you to make sure that you always simplify this ratio if you can. All right? And an example of when you would have to simplify the ratio, let's look at calcium oxide. All right, so calcium oxide, I'd have calcium, I'd have oxygen, that's a -2 and a +2. So if I just crisscross these, I would end up with Ca2O2. But notice now my subscripts, I can actually simplify just like a fraction. So if I had 2 over 2 as a fraction, I know that's going to equal 1 over 1. And so the final formula for this would be CaO. So if you're going to use the crisscross shortcut method, just make sure that you double check your subscripts at the end of it and you simplify those. Now, if I used my method, just multiplying and balancing out charges, I see that these two things are balanced out anyways, and I move directly to that particular situation right off the bat. All right? Okay, and so the last example I'm going to do with you today is actually a hydrate, and it's magnesium chloride, right? So there's my ionic compound. I can write that formula already, and then I'm going to make it a hydrate by saying hexahydrate. And so I'm going to start this out just like I would any other way. I'm going to do magnesium, I'm going to do chlorine, right? The IDE tells me it's a singular element. And so that's chlorine, that's -1 + 2. So my ratios here, I know I'm going to have to multiply by 2 there to get this thing balanced out. Even if you did the crisscross, you would have seen it. And so I end up with MgCl2. Now, since this is a hydrate, I know that I'm going to have some number of waters. And then luckily, this is really the easy part of this, my prefix there tells me how many. Hexa is a prefix for 6. And so magnesium chloride hexahydrate would actually be just the magnesium chloride ionic formula, and then you would show 6 waters attached to it, all right? So the hydrates are not all that difficult as long as you can write the ionic formula to begin with, okay? All right, so that was a lot, ladies and gentlemen. Hopefully you got it all down. If you got questions, get them written down, and then come to tutorials. Let me get that spit out straight. Come to tutorials and get your questions answered, all right? Other than that, I will see you in class.